talk about the origins of graph theory, where they started, and the very first kind of graph theory problem. So it's traced back to a city that was named Königsberg, but is now in Kaliningrad, Russia. They renamed the city, as cities often get renamed over time. But in that city, there was a river, and it had some islands, and there were 7 bridges as shown in the diagram. And the citizens of the city would often just kind of take walks around, either because they had to go deliver things, or they're just, going out for a walk. And they wondered, is it possible to walk across all 7 bridges once and only once? So could they start somewhere? It doesn't actually matter where you start. And end somewhere. They don't care where they end. But they want to take a walk that hits the 7 bridges without repeating any of the bridges that they already went on. So I want you to go ahead and try to figure this out for them and trace through the diagram with a pencil, because it will probably take more than one attempt, and see if you can trace out a route for them that will take them across each of the 7 bridges once and only once. So go ahead and try that. All right, so we're starting to reach a lot of frustration of either needing to swim or missing a bridge each time. And I heard somebody say that she thinks it's not possible and that we need something with odd numbers. Like we're missing something, or maybe if we kind of took one of them away, that would solve the problem, right? Or maybe if we added another bridge somewhere, we could solve the problem that way. But it seems like it's not possible to do with the current layout. So this is actually a problem in graph theory. Graph theory didn't exist actually before this problem. And graph theory was kind of created in an effort to try to answer this problem, and then thought about, well, what other kinds of problems could we answer with this? So this is a fairly minor problem. I mean, this is people wanting to take a Sunday stroll, right? That's not like the stuff that great math is necessarily made of. But this is the foundations of it, and then what kinds of questions can we answer with graphs once we kind of build from there. So it says, draw the picture as a graph. What we're going to do is let each piece of land be one of our vertices. And we can put them kind of where they are in the picture, but we don't have to, because remember, in a graph, it doesn't matter where the vertices are, it just matters how they're connected. So I kind of kept A, B, C, and D where they were in the picture, but you could really put them anywhere you wanted. What matters is how we're going to connect them. And what we're going to do is draw a connection if there is a bridge. And we're going to draw a connection for each bridge. So A, that little island, is connected to the mainland sea by 2 bridges. So we're going to draw 2 connections there. The Wi-Fi will catch up. There we go. And A is connected to the mainland D by 2 bridges. And it is connected to the island B by 1 bridge. C is connected to the island B, and D is connected to the island B. So this is a graph that describes the same situation. Okay? So what a graph often does is it takes a very physical thing and turns it into just dots and connections. We don't really care what the land looks like. We don't care what shape the islands are. We don't care how long the bridges are. We just care if there are bridges. That's all we care about. Okay. So thinking about yesterday's vocabulary, is this a simple graph? No. Why not? More than one connection between some points. So A and C are connected twice, A and D are connected twice. So that makes us a non-simple graph. But it is connected. It could get to each piece of land, so that's a good thing. But it is not a simple graph. So beneath that we have a definition. So we had a lot of definitions yesterday. Here's another definition for us today. A graph is Eulerian if it contains an Euler circuit. And what an Euler circuit is, it says that is one that begins and ends at the same vertex and covers each edge. Okay, begins and ends at the same place and covers each edge. An Euler path uses each edge once, but begins and ends at different spots. So what I was asking you to do is try to find an Euler path. I said it doesn't matter where you start, it doesn't matter where you end, but try to just cover each bridge. Okay, so try to travel each edge once and only once. Okay, so that's a path. If I told you you need to start and end at home, then we're talking about a circuit, which is an even harder question. So if we don't have a path, there's no way we're going to have a circuit. Okay. A graph is Eulerian if and only if. So this is going to be our theorem or our rule that will allow us to look at a graph and determine if this thing has these Euler paths and circuits. A graph is Eulerian if and only if all vertices have even degree. If every vertex of the graph has an even degree, it is Eulerian, which means there's an Euler circuit. That means it is possible to begin and end at the same spot and cover every edge once. Okay? So yes, so the ideas of odds and evens become extremely important here. So now that we have that fact, if we go back and look at our graph, what is the degree of vertex A? 5. We have 2 connections to C, 1 connection to B, and 2 connections to D, so there's 5 connections there. What about C? B? And D? So this really has problems. We need all even vertices and we have all odd vertices. So this is a big problem. Okay? To be Eulerian, meaning we have an Euler circuit, we need all vertices to have even degree. If we take that down a notch and just go for, okay, well then can we at least just do an Euler path? Maybe we can't do a circuit. Maybe we can still do a path and begin and end at different spots. The rule there is that we have 2 odd vertices and all the rest are even. So that was why this problem actually wasn't possible for you. Okay. I'm being very lenient to you today in that I told you I purposely tried to trick you on last night's homework and now I just asked you to do something that's actually impossible. So I guess I'm being quite mean to you today. I was like, you did not just do it. That is not possible.
What is the 2 odd vertices then?
If we are just going for an Euler path. So an Euler circuit means we start and end at home. An Euler path means we start and end at different locations, but we're still only traveling each bridge once. Okay, so we can't even do an Euler path here. We could make one simple change that would allow us to have an Euler path, and that would be like just knock down a bridge. If we knock down a bridge, we now only have 2 connections there and 2 connections there, so then we could do it. Those 2 places that we would have the odd vertices would need to be our beginning and our end. So if we were going to go for this, then we would need to start and end at points A and D. Okay? So for a path, you are allowed to have 2 odd vertices, only and exactly 2. Okay? 1 won't work. 2 odd vertices, one of them's your start and one of them's your end. Okay? And then you'll pass through the evens. And if you think about why this even rule exists, we're not going to go into proofs of graph theory. They're pretty interesting, and I actually enjoy them, but I'm kind of nerdy like that. But in a sense of just thinking about why this rule might be about evens, do you have any thoughts about why we might need an even degree for these things to work?
without repeating.
Mm-hmm.
So you go. So you can go like in and out.
You got it. If it has an even degree, that gives you an in and it gives you an out. Your in will give you one edge, your out gives you another edge, and you always need to be able to get in and out. So that's why we need all evens, and it's really that simple. That it only works if we have the evens, so that we can have an in and we can have an out. Right? So when we look at these graphs then, which one of these graphs is Eulerian? The second one. The second one has all even degrees. And you actually know this is Eulerian because at some point in your life you've drawn a star, right? And you start and you end at the same spot and you draw all the lines of the star. So the second one is our Eulerian one. The first one will not work. Why not? Where do we have problems? What's our degree at D? 3. What's our degree at C? 3. At B? 4. At E? At A? Okay, so we have D and C both had degrees of 3. Everything else had degrees of 4 or 2. So that means that this first graph is not Eulerian and that we cannot do a cycle, but we can do a path. Okay? Because we had the 2 odd vertices. So to do a path, what we're going to do is start at one of the odd, and I'm just going to mark on an S, so that's my start. And then I need to find a way that I can trace this thing out, planning on ending at the other one. Okay, so when you have 2 odd vertices, you can do a path. You're going to start and end at your odd vertices. But we couldn't do a cycle.
Wait, so the other one was Eulerian.
The second one is officially Eulerian because it has the circuit.
Oh, Eulerian.
Okay. The first one is not Eulerian because it doesn't have a circuit or a cycle, but it does still have the path. Okay? It's just not quite as good. A bicyclist wants to mountain bike through all the trails of a national park. The map of the park is shown. Because he will be dropped off in the morning by friends and picked up in the evening, he does not have a preference for where he begins and where he ends his ride. Is it possible for him to cover all the trails exactly once? So we can assume, since this question is in this lesson, that this has something to do with Eulerian paths or circuits. Is this question asking you to find an Eulerian path or an Eulerian circuit?
No, it's a path because it doesn't care where he ends or starts.
He doesn't care where he starts and ends because he can tell his friends, drop me off here in the morning and at night pick me up over here. So he doesn't need to get back to his own car, right? If he was driving himself to the park, he needs to get back to his car. So then we'd be going for a circuit. But since his friends are going to pick him up, he doesn't care where he starts and ends. So this question is asking us, is there a path, an Eulerian path here? So to do that, we want to count up our degrees of our vertices. So what is A? 3. B?
4.
C.
4.
C. There it is. D?
2.
E?
4.
F?
3.
G. Okay. Is it possible? Yeah. Where is he going to tell his friends to drop him off? A or F, and then pick them up at the other one. Okay. So this works with just the 2 odd vertices. It doesn't actually say what is the path. It just says is it possible. So we don't need to actually try to go trace out our path now, but we could. We would just need to make sure that we start at A or F and end at A or F, the other one.
Wait, so it's okay if it's uneven as long as there's an even number of uneven?
Only 2.
Only 2, okay.
Only 2. Yep. If you have 4 odds, that doesn't work. That's the original Bridges problem. Had 4 odds and we couldn't do it there. You need to have at most 2 because one of them's your start and one of them's your finish. And all the other ones need that even so they have an in and an out. Otherwise you get stuck there.
What if there's 1 odd?
Won't work.
So the criteria for it to be an Euler path is that there's only 2 odd vertices, but what if it's like for an Eulerian circuit, like how many odds does it need for
0.
Oh,
An
so
Eulerian
0
circuit
for
needs
the-
all evens.
Okay, 2 for path. Okay.
The floor plan of an art gallery is pictured below. Is it possible for a person to stroll through every doorway exactly once? That's not usually how I go through a gallery. When I go through a gallery, I want to make sure I go to each room once. I don't really care about walking through every doorway. But here, I don't know, they want to make sure that they're going through every doorway once. So how do you think we could approach this problem with an idea of graph theory? I mean, we could just try to start tracing it out, but if we want to know for sure, like if we're struggling to get an answer, it's hard to say are we just struggling or is it actually impossible, right? So how can we answer this with graph theory?
Either how many doorways are in each room?
Yeah.
Or you could graph a model of the floor plan.
How would we graph out the floor? What would represent our vertices and what would represent our edges? The vertices are the dots. So if I want to go through the doorways,
Oh, I know.
the doorways should be,
The rooms with the dots through the doorways would be a line.
yes, because for an Eulerian path, we're trying to cover our edges. So if I want to go through my doorways, I want to cover my edges. My doorways are my edges then. So what we're going to do is make each room a vertex and make a connection for each doorway. Yeah. So I just did mine right on top of the floor plan. You could, draw it off to the side, but we need 6 vertices. You could label them through F, and then each doorway becomes an edge. Is this a simple graph?
Wait, no.
Why not?
Because A is connected to E twice.
Okay, so it depends how you label them, but the room in the upper left, which I assume is your A, is connected to the large room 2 times. Okay, so we have 2 connections here, means it's not simple. When we start to count up some degrees, we get, starting in the upper left, what? And then moving across. And then we'll just kind of go around then. Now below that we get, the big room has I got 6. 1, 2, 3, 4, 5, 6 because of that one double connection. Yeah. The big room is connected to every room and is connected to the one room twice. So it has 6 connections. So now, is it possible to go through each doorway exactly once?
Yes.
Will we end where we started? No. Okay, so it's possible, but we're not going to end up where we started. So we're going to need to begin in one of those 2 rooms labeled 3, and then we'll end in the other room labeled 3. And that's why just kind of trial and error on this could work, but it could take you a while because it actually matters which room you start in. So if you're trying to make your path from starting in the upper left-hand room, you're not going to be successful, but then are you just not successful or is it not possible? So that's why these problems become a lot easier to answer with certainty once we turn it into a graph and take away the trial and error from it. So it is possible to do, but we're going to end in different room than where we started. So it's possible to make a path here.
Since you said like at the beginning that it's not really like what mathematicians would do to find where these go, what would you use this for? As a mathematician?
Oh, so one way, I mean, okay, so mathematicians are more concerned about when we look at these, what kind of theorems, what kind of cool things what cool questions could we ask, and then can we prove an answer to it? But then once we get into the application, this being, it used to be called applied math, and we're talking about applications. One application is like planning a route, so like this bicyclist. Like, is it possible to do that? That kind of question of like planning routes would be a way that this becomes something important. A mailman, especially a walking mailman, does not want to have to walk more than necessary, right? So if he pays attention to which streets, how could he avoid having to pass back by a street that he already delivered mail on and have to go through that street again? So that's where these could become important.